Could you please take your time to introduce yourself from?
Hong Hong, yeah. Hi, I'm Hong Hong. I spent all my life, almost all my life, developing imaging system, from the Firephone camera to the iPhone 7 first dual camera to the portal camera in Meta, and our recent product is the Ribbon Stories. Yeah, so very interested to join the discussion. I'm a fresh eye to the mobile development, and eager to be very interesting discussion to have with these two gentlemen
Cool.
here.
Thank you. I'm Zohaib Mian. I'm VP of Products at Velodyne. We make LiDAR sensors. I know there's a good support team to help me with all the noise issues that we may have. I'm an aerospace engineer, and all of my career I've spent on robotics and autonomy. I've been lucky enough to work with a wide spectrum of sensors, pun intended, and I'm definitely looking forward to this chat on cameras, LiDARs, and sensor fusion.
And I'm Stefan Heck, the founder and CEO of Nauto. My background's a PhD in neural networks and philosophy. I have no prior attachment to cameras or LiDAR, but we use both.
Nice. You have two PhDs? Neural network and philosophy?
Two different departments, but it's combined.
Interesting.
Yeah.
All right, so today's discussion is around camera versus LiDAR. I know each of them provide something valuable for the modeling, but my question is, what's the strength and weakness of these two sensors? Do you want to start, or anyone?
I'm happy to start. You know, none of you see an infrared, right? So the environment we all live in is designed for humans. It therefore is designed for visible spectrum. And so if you don't have a camera, you won't see things that humans are seeing all the time. And if you're driving or if you're doing any other critical safety activity, you have to interact with humans the way that humans see the world. On the other hand, cameras are fundamentally 2D image sensors, and so you don't have depth. You can infer depth, obviously, in lots of different ways. But ultimately, if you're going to get in a vehicle that's driven by a multiplicity of sensors, the more the better, because your life's at stake. And I'll talk more about that in a second. And so I wouldn't get in a vehicle that relies on one single sensor physics, one single sensor device, personally.
I think that's a good point, right? Sensor fusion. But yeah, I think what you said is very important. You said the world is designed for vision, so you get an RGB pipeline from the camera. That's a plus point. But again, we're pegging the assumption here that we have to operate autonomy in a world designed for automation. Good idea, right?
Yeah.
I think the strengths and weaknesses, it's not a point of contention, right? You've got really good range and accuracy in a LiDAR system. You don't have to worry about the environmental impacts on it, whether it's sunlight or it's nighttime. The weather elements are less of a consequence. On the other hand, with camera, you have cost as a huge benefit. There are billions and billions of cameras produced, any given year, versus, few thousand increasing. But yeah, so cost is a major benefit there. Plus, you've got an RGB pipeline, so you've got a lot of way to process, whether that's OCR or reading signs or things like that. So yes, the whole topic is provocative, I think, cameras versus LiDARs.
Is it?
I don't know, is it?
Controversial.
Maybe. But I think what I agree with what Stefan just said is about the fusion part. And maybe that's something that we should talk a little bit more about.
All right. You.
Yeah, so I think it's definitely a very interesting topic, right? So I think many animals actually involve when they develop the sense of the world, it's taken many years and eventually end up just with vision, right? So, and the sound is augmented like ultrasound, etc. But I don't think any animal evolved with a LiDAR on their head. Right? So,
But you have bats and dolphins, so you can kind of count that.
So I mean, there's definitely a lot of this way to develop a sense of the world around the animal, and eventually looks like all the evolution ends up with the vision system with the two eyes or two cameras, right? So I think maybe that's also something we can infer from that.
So some question actually just spinning on top of my head. The LiDAR, as you all know, generates tons of sparse data, which is not usable. How do you manage removing those?
All right, I guess being representative of a LiDAR company, let me understand.
All right.
You mean tons of sparse data? What do you mean by that?
So, for example, if you have LiDAR, it just shoots photons and then gets a reflection. It can just detect the dust in the air. So the dust is not what we're looking for. So you know how many those type of particles are floating on the air, which are not the point of just having LiDAR to detect and map the environment. How do you manage that?
Okay, so it's a good question, right? I think it really depends. The detection depends on what wavelength you are on. At the end of the day, right, whether it's cameras or LiDARs or another sensor, it's all which wavelength you are and what it penetrates. So for instance, 905 nanometer LiDAR, which is pretty common, doesn't have, it passes through most of this weather elements. Plus you've got something which is beneficial when you have an inherently 3D sensor, which is multiple returns. So let's take an example, right? Instead of dust, maybe let's use a rain droplet. You're going to shoot a laser. Not all of that laser is going to get obstructed by the rain droplet, right? Part of it may go further. So now some of the modern LiDARs actually can detect dual return or multiple returns. So what it can actually tell you is like, okay, wait, the first return that I saw is very weak. The second return I saw is a stronger return. So you can actually understand whether what the weather conditions are, but maybe that's not the goal, right? The goal is really to see where the object is, so you can ignore the first return and you can say, hey, second return is the object. So there are ways that you do this. Some of that is inherently just works out for a 3D, inherent 3D sensor. Some of those you can, of course, then you go back to your algorithms or filtrations. I mean, it's no different than saying, a radar, a couple of conversations I had where two people asked me two different questions. Like, I heard radar, you only use it for stationary objects, or radar, you use it for moving objects. You know what? You use it for both, but not at the same time.
All right.
You filter one out. You filter, if you're using it for cruise control, for radar guided, you filter out stationary, right? So it comes down to it. At the end of the day, where you are on the waves on the spectrum, and what is your use case is important. But
any other inputs?
maybe Stefan or?
Yeah, I think radar definitely is a ways to mitigate all these drawbacks from the LiDAR, right? But I think the camera may be a little bit more robust with the higher resolution, right? So rather you, for LiDAR, you only have several K points out there. If you you lost several hundred, maybe a big impact. But for camera, you have millions of pixels, so maybe have more robustness built in to process the data. But I do want to say that there's a challenging situation that can be challenging for both, like a heavy raindrop, right? So in that situation, even human driver need to slow down. But I think still have more robustness with the more high pixel camera that can handle. Yeah.
So do you? I'm sure you guys know. Do you know who said that? All we need is a camera.
It's the guy who owns Twitter now, right?
Yes, he's buying that. He's almost closing the deal. So is he crazy? Without naming him.
I'll start.
Elon Musk.
I already gave my view. I think getting into a car with only a camera is crazy.
Sure.
So I think the claim that all you need is a camera is crazy. I drive a Tesla. It has a radar and a camera. It's one of the older versions. And I don't trust autopilot without paying attention and watching. It gets me nearly killed about once a week. Because it makes mistakes, right? And by the way, I say that as a fan of cameras, right? We use cameras for the reason you mentioned, which is they're very inexpensive. For $400, we can take care of 60 to 80% of all your collisions and keep you safe. But what about the other 20, right? This is driving with the human. It's a co-pilot, so the human is still in charge and the human is still driving. The human deals with the other 20. And you've got this interesting mix of expertise. The AI and the computer vision, whether it's camera or LiDAR, never falls asleep, doesn't get distracted. But when you talk about complex intersection situations with pedestrians and kids and animals, humans are very good at inferring what are those people about to do from what they're holding in the hand, where they're looking, the relationship of the adult to the kid, et cetera. What the dog is straining on the leash, that's very, very hard for AI and either LiDAR or computer vision to understand. So you want that complementarity. If you're going to trust your life into a vehicle with no steering wheel or a other kind of flying vehicle with no no cockpit controls, you better be sure that it's recognizing all the objects. And everybody knows we've had one fatality in the AV world. In that case, they turned the radar-based safety system off, and we're relying on LiDAR and computer vision. Why would you ever cripple one sensor physics that could detect something when the others aren't sure? And every sensor device, in my view, has edge cases, right? Cameras struggle in snow and high reflectance, really uniform patterns. Cameras struggle with extreme contrast coming out of a tunnel. There's event cameras now that actually do much better in that kind of environment, but they struggle with longitudinal motion. They are great at lateral motion. So I don't believe that you should ever make a claim that says one device is enough. The real goal, the debate we should be having is what's safe enough? And then you can actually go back from that and say, okay, what sensor package do I need?
Sure. Any other input?
Yeah.
I think, no, go ahead.
Go ahead, please.
Okay. I think context is important to your statement, right? I mean, it's worth noting SpaceX uses LiDARs, right? If you're looking, and I think safety has a cost associated with it, right? So it's worth talking about it. If you look at the context where you are trying to sell a car, where 20 or 30% of that back, 7 years or so, the cost as a sensor, you would be content to say, how am I going to ever make profit on that? So what do I do, right? That's one part of it. So cost is a major thing, right? But we also know from Moore's law or less popular Wright's law, which equates productivity to the cost does decrease, and we have seen that part of it, right? You've seen 10x cost reduction in LiDARs. You're going to continue to see that trend. So it'd be very interesting, because Stefan described a lot of valid points here. So I don't want to rehash those, but it'd be very interesting to see if cost was not an issue. If we get to the point where cost is very similar, would that statement change or not? Right.
That's a good segue. My next question was, all right, let's say now we have the evolution that we see. LiDAR used to be close to $100,000, for example, a good LiDAR. Now it's getting, the cost of LiDAR is going down and down. I don't know for any reason, but with the good quality data that you can get, it's around six grand, for example. So let's say we don't have that kind of cost barrier, and a camera is as costly as a LiDAR. Which one would you guys pick for implementing? I know you're just looking at me in a way that no, it depends on the use case. Which one is more accurate? Which one is more applicable to, for example, self-driving car?
Maybe I answer that a bit also
Okay.
with the previous question, right? So I think from principle point of view, right? So I think a human and all this, they operate the car, like I said, with just the 2 cameras, right? So I think there's many ways to achieve that goal. Maybe it's a 2-camera plus on LiDAR or something, but at least from first principle point of view, it's already proven that a human can do that, right? But I think also a lot of that in the details that could the current camera technology match the human vision, right? So to handle that. I think we are very close on that range, right? So if you look at the human vision, I think to translate to equivalent camera spec, it's about 170 degree of FOV and also 50 mag, right? So that's about 20/20 vision for human. And I think current days technology is very close to offering that. I think dynamic range is another important one. I think humans have a dynamic range of 144 dB. And I think current days camera technology is not all the way there, but I think it's approaching there. And then look at the compute. I think human brain is about 100 teraflop, right? And also I think recent Tesla SoC can also provide something very similar in the compute power. So personally, I do believe that in the near future, from both sensing and compute perspective, we are reaching that capability, and then it's the problem, how do we develop all these the algorithm, etc. to do that. But I think it's also no denial that the additional sensing can help, but how much help, I think is unknown factors.
Yeah, because I personally, we at our company killed many projects just because of the cost of LiDAR. But that is essential to just implement that type of projects, and that's why I'm asking that. So, because you're just giving me a very dirty look, I'm going to ask you this question.
I was going to tell you, I thought that was the wrong question, but go for it.
Yeah. So, so you talked about that 20%.
Yeah.
So how do you solve that 20% with the accuracy that you know now from camera and LiDAR?
Well, I think, again,
Adding more LiDAR?
Adding more sensors of different types, yes.
Different types.
I mean, you phrased it as one camera, one LiDAR. I think that's the wrong comparison. I think the question is, what's your total sensing budget? How much is enough to achieve safety, right? And if we pull this room, how many of you would get in a car that's just as safe as the human driver? None of you, interesting. Maybe a few hands here. How about 4 or 5 times as safe as the average human driver? Okay, more of you. So what if it was 10 times? Most of you? Okay, so there's the implicit psychological threshold, right? So then the question comes, okay, by the way, most AVs have not just one LiDAR, but 5 or 6 or 7, right? Good for your business. Most of them also don't have one camera. They have 15 cameras, and I think that's realistic. The question is, how far down that curve do you go? Today's AVs, if you look at the public data collected by the California DMV for all AVs that are driving in California, they have 4 times more collisions than the average human driver. Most of you probably didn't know that because it's not well publicized. Right? So don't get in those yet, is the answer. But what's interesting is if you take the average human driver that I asked you about versus an attentive human driver, they're twice as good, half the collision rate. Now take the best 10th percentile, right? The top 10%, mostly commercial drivers at that point who do it as a profession. They're actually 10 times as good. And what's the best human driver? We have 6 drivers in one of our package delivery fleets that have driven for 43 years without having a collision. Think about that, an entire lifetime without a collision. That is way better than any technology today. So where's the bar? And to me, that's the real question. Okay, what's the ethical vehicle, and when do you let it out on the road? Do I spend $1,000? Okay, I can buy a lot of cameras. I can buy half a LiDAR today. Eventually, I might be able to buy 3 or 4 LiDARs and 6 or 7 cameras. What's enough? And I would argue today, if you're doing it with 2 or 3 cameras today, you're not being responsible. And that's where I disagree with the assertion that camera's enough.
I'm not making any claim. I'm just trying to
of course.
Learn from you.
We're just
This is just a conversation.
Making it
what
entertaining.
What about the learning curve? Which one is easier for developers to adopt? LiDAR, camera. We know camera, people are just using computer vision on frames of video that they receive and do the computer vision modeling, all sort of things for object detection, video, and analytics. So what about the LiDAR? Most of scientists in the field are kind of afraid of just processing LiDAR data. What do you guys think?
All right, maybe I'll give you my take.
Okay.
And for what it's worth, sub 1,000 LiDARs they're around the corner, if not already available. You should talk to, I'm not going to say any costs. I'm going to get in trouble with my marketing department. But there's certainly, the cost is going down, right?
Okay.
So you mentioned learning curve. I think there are 2 things to look at here. One is the hardware development curve, right? Which is what I was associating with Wright's law. Which essentially says every time you double production, your efficiency increases by an X%, right? Wright, Theodore Wright, was in the 1920s and 30s, he realized that was happening with airplanes. So he looked at it and said, you know what, every time production doubles, 15% reduction in the cost. Versus Moore's law, which goes over time, right? Mm-hmm. So that's part of the learning curve. Now, having worked on perception stacks using multiple sensors, honestly, it's agnostic to me. Velodyne itself has a perception stack that uses LiDAR data to do object detection and classification. The effort that you're going to put on developing an algorithm is irrelevant, in my opinion. Whatever effort you're putting on the camera, you can put on the same thing. It's how you're setting up your system. If you start with one type of architecture, and then you start, when you're further down the road, then you start adding more components, yes, you're going to have to go back and make some changes. But I don't think there's an inherent difficulty on a data stream coming from a LiDAR versus a camera, in my opinion. it's agnostic to that. Of course, I think the aspect is what do you use for what, right? So we're talking about sensor fusion, and that's part of redundancy, which adds to the safety case. I mean, I think right now there are some companies that are already doing pilot testing. Really, the question, in my opinion, they're answering is, how do we close our safety case? What is the safety case, and how do we actually prove it? Because we have seen the regulatory bodies are essentially saying, industry, lead it. You don't need a steering wheel in your car anymore, right? Very recently, NHTSA made that announcement.
It's called self-certification.
Exactly, it is self-certification, right? So with that said, I think the question again comes down to, what is that safety case you want to build? And you can, based on that goal, as part of the rest of your business goals, you figure out what the package is, and then you build on it. So if cost, or if it works for me, and again, depending on cost, like if your system that you're producing is much more expensive than a car, maybe $1,000 LiDAR isn't bad, especially when you're looking at a lot of safety issues, right? Like SpaceX example that I gave. You know, millions of dollars of rocket, you put LiDAR on it, right? And you build on top of that. And yeah, I think let me see what you guys have to say to that.
Go ahead.
Yeah, I think the sensor fusion that was an interesting topic. I think that depend on the situation. I think each sensor, basically it's a probability of accuracy, right? So I think that's both corner case for camera and for LiDAR as well. I think that find a way to combine the best from both. I think it's the potential I think benefit of combining both. If I can find an algorithm to effectively leverage both use case in the best scenario.
Yeah. I'll just add, I think the real expense is not in the tool chain of one or the other. You know, they're both evolving rapidly. The LiDAR tool chain, I think, has progressed a lot since the early days when it definitely was harder to use. But the real question is, how do you collect enough real-world data to actually know that you're safe? And a quick back of the envelope, 8 years ago, that RAND did was, you know, billions of miles of data are needed, I think, to really get to the level of 99.9, which is close to the best human drivers, not even reaching that. You're talking about something like 200 billion miles. So Waymo's driven 30 million. Most other AV companies have driven a couple 100,000 miles. Nobody's in the billions. Right? We're not close to the level of data to know I've really covered. If you look at fatalities, they're 100 million miles apart. 100 million miles, right? So we're lucky to have seen one AV fatality, lucky in the sense of data collection. Because statistically, that accident shouldn't have happened. It was clearly careless to operate the vehicle that way. And so how many more people are we willing to sacrifice before we really have technology that we want to scale? On the flip side, we're killing 42,000 people a year in the US, 1.2 million globally. So it's not like doing nothing about the problem is going to help either, right? So how do we get out there with this technology in a safe way? Again, we have a particular solution to that, which is to keep the human driver involved until the technology really gets to that point. But there's many other ways to solve that. You can simplify the problem, do low speeds, shuttle service, do only dedicated lanes, do long-haul trucking at night. So there are other ethical ways, I think, to solve the safety problem. But if you look at the real expense, it's not do I add 5 cameras and 3 LiDARs or half of that. It's really how do I make sure I've proven my safety case for all the real edge cases that are out there. The last 3% are much, much, much harder than anybody in the industry is willing to admit. And the realistic AV, yes, it will reduce 80, 90% of collisions, but it will introduce 2% new ones that a human wouldn't have had. In our current legal system, that's a huge problem because you're going to get sued for those 2%. And by the way, it's not just a problem for that manufacturer. As we saw, Arizona went from please come run all your AVs here to please keep all your AVs somewhere else. And that's going to happen. The first time we have a fatality in California, guess what? It won't be self-certification anymore. It'll be proof to me that you're actually a responsible operator.
One more question I have, and then we'll open the floor for questions. All right? So you just touched on AV. Let's just talk about the timeline of AV, and what does it mean to be deployed. So anyone want to just take on that question?
I'll start out. To me, AVs, what does it mean when it's ready, when it's deployed? It's the same kind of fallacies when people talk about grid parity, right? Solar has had grid parity in Africa versus diesel fuel for 20 years. California, we had it a decade ago. In other parts of the world, it's coming. So to me, when are AVs ready to deploy? The right answer is, what's your use case? Right? Running a closed loop on a shuttle on a known campus that you can highly map, where you can deal with difficult intersections by instrumenting the intersection, the physical infrastructure, and you're doing it all at 10, 15, 20 miles per hour, sure, that's going to happen really soon. Right? Running between Houston and Dallas on empty highways under the right conditions when there's no winter storms, no rainstorms, et cetera, that's happening today as well, right? And, but what everybody kind of imagines, if I get into my car and I say, take me to my grandmother, and you're watching a movie the whole time, not anytime soon, right? I think it's been 10 to 15 years out for the last 4 decades. And so, I don't know if you guys disagree, but I think we're still 10 to 15 years out for that really take me anywhere under any conditions.
Any other inputs?
Yeah, sorry. I think I agree that the last few percent is really the hardest one, right? So it takes maybe you take 99% effort on last few percent.
Yeah, I've been hearing 5 years for the last 15 years. So it keeps happening.
I'll record it. I'll get back to you on that.
Yeah, let's talk about this in 5 years and see where we're at.
Remember, the guy who said only cameras also said he's going to sell us AVs that are full self-drive, on autopilot in 2019.
I know.
Now we have full self-driving. Eventually we have whatever he's going to call it next.
But he fulfilled his promise. He bought out the social media.
So I think one point here,
So hold on.
what Stefan said is really important.
Yeah.
Which is the ODD, right? When you say when will AVs be deployed, it really comes down to what your operational design domain is. And you can have it as narrow and as wide as you want. What we're going to see first is very narrow ODD being deployed, and then it needs to prove economic value to it before further driving happens. Now, one reason, why, just coming back to camera versus LiDAR, why I would want to have LiDAR in a car is to what you said, 30 million miles and 200 billion miles, that's an exponential difference. It's not, it doesn't sound as much, but it is. And I remember there was a presentation earlier this morning where we're looking at number of seconds, and it was showing how many years it is, right? Similar concept. So this whole conference, we've been talking about computer vision and data, right? So you take data, you put in a neural net, you get some answer, and then you use that to make a decision. So we put this on an AV, and one of the most safety case issue is you need to detect an object, and you need to be certain about that object, right? CV pipeline, you are using a sensor that's not inherently, if you're using it standalone, not inherently built to provide very accurate object detection and range distance information by default. You do tremendous stuff like this. Computer vision has come so far that it's amazing what we can do. But whatever result you get, there's going to be some uncertainty bounds. And those uncertainty bounds will move from situation to situation. So now if your car has to make a decision based on that to say, hey, is there a car in front of me? Is it 10 meters? Is it 15 meters? Is this uncertainty bound 5 meters or is it 1 meter? Makes it very difficult. So you can end up in a situation where you're very conservative. The car behind you is like, why is this car not changing the lane? Why is this car not moving? Or you become very aggressive, which could lead to more accidents or so on. So the benefit of the LiDAR, why I would always use it, at least for now, it takes that, it puts some certainty bounds on your object detection and ranging. Right? So that's one part of it. So to wrap this up with that connects to a safety case. Goes back to the issue. Deploying AV, prove your safety case. Every company is responsible to do this right now until it becomes standardized. And then only you can say, okay, what economic value we start getting out of all of this funding and money put into this domain.
Great.
2 quick comments. One is on your ODD. I'll give a really simple example of what ODD means. I don't know if any of you have ever flown into Zurich, the airport. You take a train from the terminal to the main gate. You hear all these cows on that train because they go moo, they're welcoming into Switzerland. That train has been fully autonomous for 20 years. It's an extremely small operational domain, right? The same track back and forth, fully autonomous. So yes, we have had autonomy for quite a long time if you measure it that way, but the ODD has been this tiny use case. The other thing I'll say is you gave the example of LiDAR giving you a second source to reduce some of that uncertainty. The fact that AVs are hesitating is why they have 4 times more collisions than other people. They're getting some pedestrian interactions wrong, so they hit pedestrians or bicyclists because they're unpredictable. The other thing they're getting wrong is they stop in unusual places where the other drivers don't expect the vehicle to suddenly stop. So they're getting rear-ended substantially more than human vehicles are, because the default when you don't know is to play it conservative. But conservative does not mean safe. Conservative means I stop when I don't know, but that is actually not a safe thing to do on most roads. Classic example, almost every AV in the world slavishly follows the speed limit. What's the safest speed to drive on a typical road, whether arterial road or a highway? The speed of the other humans, which, by the way, road engineers design roads for everybody on average to speed by 10% above the speed limit. The engineers already know. They design the road, they post the speed limit for you to speed a little bit like everybody else, and then you're actually safe. So now if you have an AV in the middle of that, guess what happens? That AV slavishly goes 55, everybody else has to pass. What's the most dangerous maneuver on a highway? Overtaking maneuvers. So you're introducing risks. That AV won't be at fault under the legal system, but actually that AV is introducing extra risk for everybody else who has to overtake that AV. So those are when people talk about the trolley problem, that's the real trolley problem. Like, what's the social societal cost that we're imposing for having these vehicles out there? On the flip side, what's the societal cost of not getting computer vision and LiDAR out there to actually improve safety? Today, we're killing a lot of people with, driving around. For those of you who are between 15 and 50 years of age in this room, which it looks like is almost everybody, your number one mortality risk is a car crash. Number one. If you're younger, it's suicide. If you're older, it's heart disease and cancer.
All right.
Now maybe you want to end the panel.
Thank you. I really enjoyed this conversation. So let's give a chance to our audience to ask their questions. So first you, please.
Yeah, I found this to be a very interesting session panel here.
Do you want to take a mic?
I found this to be very interesting, so thank you for being up here. You guys are certainly experts. The one thing that I found unusual is the time allocation to full self-driving. So I'm assuming that you're thinking level 5, right? Full autonomous. In the back of my mind, I was like, oh, probably about 5 years, because a lot of this is not about what the camera or the LiDAR or the radar sees, but the judgment behind what should I do based on what I see in that situation. And so my question is, when you were looking at, when you're making this assessment, if you look at companies like Tesla, which have a very advanced neural network focusing on the judgment factor more than the information gathering device, whether, so I'd just kind of be interested in hearing what you guys have to say about the justification around the 10 to 15 year mark for full self-driving level 5.
Yeah, to me, it's less about full or partial driving, level 4, level 5, level 3.
Yeah.
It's more about what Zohaib said earlier, which is what's your operational domain that you're good for, right? Again, using the Swiss train example, in that narrow domain, we've had self-driving for 20 years. In the domain of low-speed shuttles, we have self-driving today, right? You can go to Florida and in a retirement community ride a shuttle.
Yes.
In Phoenix, Waymo has been operating very well at relatively low speeds in low pedestrian, really huge wide streets, safely for several years now. And they haven't had a serious injury or fatality collision.
Controlled environment.
Yeah. Simplified environment is what I would say. It's not controlled because it's not like it's private property, but it's a simplified domain, right? And so to me, when I made that 15-year projection, and by the way, I didn't think it would be solved in 15 years. I think it's always 15 years out, is the full unconstrained version, right? Which means I got to deal with snow. I got to deal with crowded urban areas. I got to deal with animals on the road if you're talking about the Midwest or if you're talking about developing countries. I've got to deal with pedestrians who break the rules, who jaywalk, right? If you look at New York is red is run and green is walk, and there's pedestrians everywhere, right? And so what do you actually do to do a turn in New York? We all do it when we drive in New York. You negotiate. You inch forward until there's a little gap, and then eventually you play chicken with the pedestrians, and they pause, and then you go through. very, very hard maneuver. It's a communications maneuver, right? So most AV companies treat autonomous driving as a physics problem. I've got to move my block through a bunch of other blocks. I'm simplifying, but basically, right? And if you look at urban driving or the kind of complex intersections, it's a conversation. It's a turn-taking game, which humans are extremely good at, and AI is not yet good at. So,
are you thinking it's going to need to be more general AI to understand the psychology of how humans think in order to be able to adapt to those situations?
I will wager one prediction. I don't think we'll have a successful urban AV under any conditions until we have AI in the vehicle that understands human motivation and intent. It will not be full general AI, which is a much higher bar. But you'll have to at least understand, what does the guy who's doing this, what's he doing? And when he's doing this and walking at the same time, what does that mean? And so forth. So, yes, absolutely.
More questions?
Thank you.
You have two.
Do you disagree?
No,
Yeah, thank you for the panel. I would like to expand my topic, pull the topic away from EV, more like in simultaneous localizations and mapping. I know there are systems, LiDAR systems in the market that cost actually quite a lot. So a lot of people or companies are looking into using camera systems to do SLAM. From my experience, I always adore that the LiDAR is providing the millimeter level or centimeter level accuracy in terms of the mapping and locationing. Meanwhile, camera is a much faster, less cost, but performance-wise, it's not as competitive. So, do you think is this difference is governed by physics, or is it just that we haven't really got the hang of getting the camera to the same level as LiDAR?
Who's taking that question?
I think you should take that one.
it's the camera.
Aren't you guys doing AR?
No, I think it's a different type of depth system, basically. Right? So I think the aero budget for the different depth system is different. I think for the camera-based, basically stereoscopic depths, I think the aero is like exponential, right? So in the short distance, definitely have an advantage actually over the linear system of LiDAR, which is, I think aero budget for a LiDAR type of laser is more linear, right? So I think in the short distance, actually camera-based system have advantage. And in the far away distance, like a 10 meter or something like that, definitely is LiDAR have a much lower aero budget for that. Yeah.
I'll add two other data points because we did do SLAM with just a camera-based system. People miss the fact that motion actually helps because you're getting different angles on the same object. And again, going back to the environment is designed by humans for humans. Stop signs are all regulated sizes. You know exactly the shape, the dimensions, everything to them. So you can use those reference objects as a way, and they change orientation. Second thing is, going back to the cost point we started this conversation with, if I have 10 camera passes, I can actually get down to centimeter accuracy. We found we get to centimeter accuracy in 8 passes on average. Now, one LiDAR pass will get you there faster, but depends on the cost of that pass, right? If you're running a $200,000 mapping vehicle, sure, you only need to do one pass.
And the third point is the absence of light. You can't just use, the cameras are useless in those cases, right?
That's right.
I mean, yes, environmental conditions affects cameras. I mean, that's also part of the uncertainty too, right? Shadows, sunlight, is the same way we can get fooled.
All right, we have questions from Ryan. Now you know your name.
Thank you so much for the discussion. It's a really exciting topic. And I have worked with LiDAR a lot, in the sub-training environment and also in the room environment. So I appreciate the technology. But what is happening to the industry? We see real sense, right, is becoming discontinued. We see, structure sensors are discontinued. And I know these are not LiDAR like the Velodyne, but there is something called, like in space, we have COTS, SWAP, which is cost, size, weight, and power constraints. And that's really important, like the size of the hardware that you want to use is critical. And maybe that's why we see cameras are widely available because of these constraints that they respect in different applications. So where do you see the technology for LiDAR is going, and what's happening with the LiDAR scanners? Do you see any path for growth or improvement in this area, like cameras that we saw in the past decade?
Sure. I'll take that. Okay, so let's start with the cost, right? I think Velodyne announced a $100 LiDAR, but I think $100 LiDARs are not too far. We'll certainly have those, right? Same thing with the sizing. Like I was mentioning earlier, cameras have been around much longer. There is economies of scale in its favor when you're building billions and billions of cameras. I mean, every phone has like 4 or 5 cameras. I don't know, you can get like some phones that have 10 cameras. So that all helps to it, right? LiDAR is relatively very young technology. So, but there is growth. What you are seeing now, where you're going from directional rotating LiDARs to solid state LiDARs, to things that use MEMS technologies or scanning mechanisms. I mean, Velodyne came out with, and this is not a plug at all, it's the only example I know, so that's why I'm giving you that, micro LiDAR array, right? Which is essentially you're converting your laser engine into an optical chip technology, which is analogous to semiconductor, right? Still early on, the cost is going to keep getting reduced. So like I said, I think a $100 LiDAR or sub-$1,000 LiDAR is much closer. $100 LiDAR is not that far, and you're going to start seeing a lot of those coming in. Now here's the other thing too. You know, I can't really comment exactly on these other products that you mentioned. Everything is based on cost, right? Economics drive everything. So economies of scale are really important for any of these sensors to continue going. If you can replace something with cheaper, with almost similar performance, you will naturally do that. I think CV, computer vision pipelines and algorithms and your compute power, right? I think with camera, yes, it's fast, but it's a lot dependent on your computational power. 10 years back, it was not possible, right? Or less possible. 15 years back, you wouldn't even think about it. Although neural nets have been around since 50s, something like that, you just couldn't do it. So it is that the whole technology is moving forward, whole stack is moving forward, and some things are becoming obsolete because they apply to the constraints of computation and cost at that time, and some things are continuing ahead. The way that I see it, the LiDAR technology itself is improving. There are a lot of sensors that are coming out, same thing with packaging. There are LiDARs deployed on road consumer vehicles now, which are not those round circular things that you would see. They could be embedded in, right? So for sure. And that's a place I strongly believe that. And I can't wait for the time where I can just go and buy a bunch of these LiDARs from my house, put them out, like next to the cameras for security cameras, because why not, right? So that's my take on it.
All right, let's take one more question and then break for coffee break or tea break. Sorry, this time
It's 4
tea.
o'clock, so we got
Right,
tea.
go ahead.
So my questions are going to be quite simple. One is I agree with Stefan about the safety aspect of it, right? I mean, we are at like assisted AI and augmented AI or whatever levels in different organizations. Getting to general AI is, I would say, even 50 years away, right? So from a full human being capability standpoint, we are not going to see that soon. So what level of advancement are you looking at when you say safety and the ability to get all these autonomous vehicles out on the road from a regulatory standpoint?
It's a question for me?
Yeah.
Yeah, so I mean, as I shared, today with computer vision alone, blended with a human driver, we're able to get to the level of the best 10% of drivers, right? So we can get you a 70% reduction roughly in collision frequency.
Right. So a human being driving, assisted with
Correct.
A technology, is definitely going to be better than just the human driver, right?
Sorry,
Because
is it?
So the human driver, like I
Yeah.
drive a car,
Yeah.
I don't have any technology, let's say,
Yeah.
and I drive without any kind of problems. If I have technology to assist me, it's going to be better than my driving without any technology. Is that a fair statement?
Well, so I'll give you the exact spectrum. The average human driving will have about 20 collisions over 1 million miles of driving. Very few people actually drive 1 million miles in their life, but if you drove that much, that's how many collisions you'd have. The attentive human being is about 40% better than that. So just by putting your phone down, not dealing with your kids in the back seat, you are already going to be twice as good, right? So plug for everybody to please not text and drive and put your phone down. If you look at traditional ADAS technologies, what people refer to as level 2, right? Your forward collision warning, your automatic emergency braking, the best of those, automatic emergency braking that has camera and radar sensor fusion. There's a study from Insurance Highway Safety Institute. It's about 28-29% reduction in collisions. So it's a third. So it doesn't even reach to the level of a good, attentive human driver. Now, if you take what we're able to do by coaching the drivers and giving them feedback on the risk behavior, all we're doing is warning you if there's an imminent collision and giving you feedback if you take multiple risks. Because the thing people have missed is 96% of all collisions are human error. So all the AV community is looking outward at the physics problem of what am I hitting, when in fact the real driving problem is sitting in the driver's seat. The drivers forget and miss something. And the other piece people haven't analyzed, because insurance companies don't collect the data this way, it's not single factor risks. It's not, oh, I'm smoking, so I'm 50% elevated risk, which is true. Oh, I'm using my cell phone, it's 2.8 times normal driving risk, just holding the cell phone up, fine. Where it gets really interesting is you're speeding, 2x normal risk. You're tailgating, depending on how close you are, 2 to 8x normal risk. You're using your cell phone. But each of those arithmetically added is about 10 times normal driving risk. The actual data is it's 400 times normal driving risk. So what do? We intervene when these exponential risk factors combine and give the driver feedback. Here's the interesting insight. Why are these human drivers not better already? They're taking the risks unconsciously. If you take a driver that has run a red light, 80% of the time that driver will not know they've run the red light. How do they know? Somebody honks at them or somebody hits them, right? That's how you get feedback that you ran a red light.
Or you get pulled
People
over.
generally, or you get pulled over, yes, that's right. Although that's the rarest of them all, I think. So the reality is most of the driving risk that most of you take is unconscious risk that you're not aware of. And we won't do the poll here. I don't want to embarrass anybody, but if you ask people how often do you text and drive or use your phone or look at maps or watch a Netflix show while you're driving, the data is surprisingly high. It's like 80% of people. And if I ask you how long do you think you're typically on average distracted while you're driving, I guarantee you the estimate in the room will be somewhere between 1 and 3 seconds on average. And I can tell you statistically in our data, the average is between 8 and 11 seconds. 5-6 seconds of distraction is a football field length at highway speeds. Right? When we have fleets of 20, 30,000 drivers, they're doing 150 trips to the moon every year without looking at the road. Think about that, 150 trips to the moon without looking at the road. And by the way, these are great drivers, right? They're way better than average, but they still have that much distraction. So to come back to your question, the technology can improve you a little bit automatically. AVs will certainly go further eventually, but the real question is, can we get those gains today much more rapidly? And again, my view is, you got to put the human and the AI together. And by the way, I think that's not just an answer for the autonomous driving domain. I think if you look at other applications of AI, humans and AI together are always going to win over just AI, over just human, whether that's medical diagnosis or efficient economic policy or whatever you want to have. So that's really the question we should be asking. How do we make progress? And it's not actually, going back to our panel, this sensor or this neural network architecture or that neural architecture. It's how do you define the problem as a system problem where you're actually trying to make progress. And to me, that's the ethical call to arms. How do we get these 42,000 road deaths off the road as quickly as possible? We accept the fact that we have our children killed in drunk driving and in distracted driving collisions. That's a choice. We don't make that choice about many other risks. And why do we let this one go?
Agreed. And that,
Right.
as a
Hold
segue,
on. So we are running out of time.
just
Please
one,
reach
it's
out.
a segue into the other little
Please
question
reach
about
out to
this.
the panelists during the break time. So we run out of the time, 5 minutes. So great discussion. Please come back in 25 minutes. We're going to have another session. Really appreciate it.
Thank you. Thank you. That was really good.
Thank you.